hold-in logic or the set reset instruction to incorporate it into the motor control. Later, we want to see what if we want to introduce a siren to our motor controller. What if we want to introduce a timer? You know, what if we want to introduce a timer, a siren, and a flasher? Okay, so what we are going to do is to be building up our design step by step as we understand different concepts of PLC. So today, I want us to, let me just give a typical question. Okay, here I said it's an example. It's a typical exam question so that you know how these questions are also approached. So it says, create a PLC ladder diagram for motor control. Utilizing hold-in logic. And it also says incorporate a start push button, a stop push button. So this is the design specifications, a motor thermal overload, okay, and a motor run contactor. So a very typical question that you might find, because I told you a lot of the questions that you'll be having in the exams are not really theoretical. That you're expected to understand the theory, but you'll be asked to apply that information to do a lot of design work. So you're expected to think outside the box. All right, so let's look at the question again. Usually it's important. I know, sometimes in an exam setup or maybe any other setting, you're in a hurry to read through the question and provide a solution because of time. But the key lies in understanding exactly what is expected of you and looking at all the different components that are provided so that you don't miss out on anything. So here, of course, we had to draw a ladder diagram. That's for sure. But we are supposed to use a hold-in logic. If from our previous discussions, we said that there are two ways of using the hold-in logic. One, I mean, not of using the hold-in logic, but of the set-reset logic. And one of them was to use, of course, I meant latching, sorry. Two ways of latching a circuit. One was using the set and reset. Okay, we did that in the previous class. And then the other one was using the hold-in logic, which we also did in the class and justified why the hold-in logic is a more appropriate method, especially when you are optimizing your circuit. Okay, so the hold-in logic is also called the logic latch. So two ways to achieve latching: set and reset, or hold-in logic, which is the logic latch, which is what we prefer. And to just jog your memory, you can see we agreed that the only way to achieve it is to have your components in one rung. Then we make sure that our second input is a normally closed contact, meaning it's going to provide a negation at the point where we expect, because remember we said that latching is basically trying to first, number one, set the output to a logic 1 or a logic high. Number two, hold on to that state until a condition is met. That condition is always met by the second input. That means until that condition changes its state. And then it returns the output back to the original state, which was false. Okay, so hold the output to true. Okay, sorry, set the output to true, hold on to that state until a condition is met or a certain instruction occurs, and then return the output state to false. And that was also achieved by branching out the output with the first input A. So I don't want to dwell on this much because that was the subject of our discussion. But now, because our question now asks us to incorporate this, I want you to pay attention to see. It doesn't mean I have to copy this circuit and paste it on my solution. No, we must understand the working principle of what has been asked. So let's go back to that. So we are to create a PLC ladder diagram that controls a motor. We use the hold-in logic, but we must use a start push button. If I were you, you'd already be thinking, where would the start push button be? The start push button is the one that is probably going to be responsible for making the output go to 1, because it is the start push button that you press expecting the motor to run. So for the output to go to logic 1, it's the start push button that needs to translate into a logic 1 or a logic high or a true. So if the start push button is true, then you expect the motor to run. Then you have the stop push button. You need to remember from the concept of the hold-in logic, it's the stop push button instruction that should return the output back to 0. Because remember, there were 3 conditions. I've not started giving you the solution. I'm just reminding you about latching, because this is what you need to understand. So 1, the output needs to move from false to true. Okay? Then we need to hold the true state. And then we need to have an instruction occurs. So a condition or instruction, in this case, instruction occurs, okay? And then the output moves back from true to false. This is basically latching. This process here, the first step here, is basically using the start push button. Because if you press a start push button, you expect the output to go to logic 1 or to be true, and then the motor starts running. The hold-in condition here, where you're now holding the true state, this is where you branch the output. You branch the output to the input. Okay? The condition that must be met, should be using the stop push button, because it is the stop push button that should be able to reverse the state of the output, so that now the output goes back to its original state. So you can see clearly that whatever we are asked to incorporate makes a lot of sense. Now, the other thing that's mentioned here is the motor thermal overload. Of course, typically, as a fail-safe measure, all equipment are required to have a safety mechanism. So that's why we have a motor thermal overload, and it's always inbuilt into the system, okay? That doesn't miss. And then, of course, a motor run contactor. So a motor run contactor is basically the output, because remember, I gave you a diagram previously for those who already remember. So if you have your ladder diagram, for example, and that's the output, then you have the output module there. Then you've got this. And so this is what goes to the, so if let's say this is output Q 0.1, then this address is also Q 0.1, because this is now the starter or the contact. This is now the contactor in this case. In this case, it's called a contactor, not a starter. So this is probably the contactor. So this contactor is the one that's now responsible for actuating the physical motor. So, but at least now you understand why each of these components is important. And so the idea is the more questions you approach in this manner, the more you will understand because whenever I give you a design problem, it's not something you expect. It's something you expected to think quick on your feet and understand, because all the information will be provided. You just need to understand where does each information fall. So how do you solve this problem in a typical scenario? So let me just try and provide that. I told you we'll build the solution as we go along for several scenarios. So the first scenario is just to use a holding logic. So before I give the solution, I also want to remind you, because again, just to make sure, even for those who are not in the previous class, we agreed, and we must understand this as part of the question. We agreed that when you wire up the inputs to the PLC, the start push button input is wired as a normally open contact. The start push button, the field device, is considered a normally open button. So that when the start push button is pushed, it changes its state from false to true. I mean, from 0 to 1. Okay? So we know that the start push button should always be a normally open contact. Okay? And that, what I mean is, the start push button is this one. The push button, not the PLC symbol. Don't confuse them. The start push button is this button here. Okay? So it's connected to the PLC. So maybe I can even put it like this. So it's clearly normally open. Then it's connected to the PLC. Okay? The stop push button is this. So you can see, for this case, the stop push. So this is start. This is stop. So this is already closed. You can see it's normally closed. The overload button, or the thermal overload button, because it's inbuilt, it's already a normally closed contact like that. So that if you press the start push button, it changes its logic from 0 to 1. But if you press the stop push button, it breaks the contact. So it moves from logic 1 to logic 0. And that's the same thing with the thermal overload, only that the thermal overload you don't press. It's inbuilt to detect overcurrents, and if there's a threshold that's exceeded, then it automatically opens, meaning then the logic changes from 1 to 0. And we agreed, therefore, that if I were to connect this to a symbol, the normally open contact, I connect it with a normally open contact. So that if I push the start push button, it changes the logic from 0 to 1. So then this moves from 0 to 1 as the output, which is then sent to the output. Okay? We said that if I were to connect the stop push button, I also connect it to a normally open contact. Because remember, the essence of the stop push button is to make sure that the logic here is 0, so that the motor stops running. So to ensure that the motor stops running, we need a logic 0 at the output. How do we get that logic 0 at the output? Remember, the stop push button is normally closed, meaning it's already passing or allowing logic to pass through. So if it is pressed, it breaks the contact, and that logic now becomes 0, so that it sends a 0 here. So if it sends a 0, then of course, you still get a 0 at the output, meaning that this contact, the normally open contact here, is not activated. So if it is 0, then you just get a 0. And like in the first case where it changes from 0 to 1, so this guy is activated, and therefore it gives you a logic 1 at the output. And the same thing happens with the normally overload, the thermal overload, that you connect it with a normally open contact, though it is normally closed. So that in case there's an overcurrent, for example, or the temperature, it could be thermal in this case, or the temperature exceeds a certain threshold, then of course it breaks contact. So you have the logic moving to 0. So if you move a logic 0 to a normally open contact, you simply get a logic 0 at the output. And so the output becomes a logic 0. And so in these cases, the motor needs to stop. Okay? So the motor stops on two conditions. Either you press the stop push button or there's a thermal overload. So I hope, again, I have overemphasized this because previously I've seen a lot of students make mistakes because they think of a stop push button and they just say, okay, let me use a normally closed contact. And the problem is if you use a normally closed contact and the stop push button is also a normally closed contact, then you're going to negate the process, meaning the output would be 1. Whenever you press the stop push button, you get a 1 at the output. So it's like the motor will be running whether you press the stop push button or not. So I hope that is also clear. I've just explained it again for the sake of students who probably did not attend my previous classes. So please pay attention to that. Keep that at the back of your mind because it will form part of the solution that we are going to carry out as we go along. So in fact, we usually say that the rule of thumb is that any device that is required to stop the motor should be a normally closed contact. Okay, any device. So you wire the motor stop signals to a normally closed, but you use a normally open symbol in the PLC. So the field device is a normally closed contact, but you use a normally open symbol in the PLC. That is the only way the motor will work as required. Okay, so back to the question. What would I need to do? Step number 1 to solve this, because you have to do things in a particular order. Step number 1, you need to list all the inputs and outputs. Okay? All the inputs and outputs need to be listed down properly. And don't take it for granted. Don't think that you'll go back to the question, read them from there. You'll miss something. You need to put them down. Now, you can quickly see that if you are just to list without having to do much, you're just listing, you don't have to we'll go to the next phase. Then you'll have your inputs as, of course, clearly we've talked about field devices. You're listing all the input field devices. So the input field devices are, in fact, I should say, list all the input and output field devices and output field devices. So the input field devices are, number 1, and this is from your basic knowledge of PLC from the beginning. We gave examples of what these input devices could be. It could be a start. In our case here, you look at the question, we see that a start push button would be at the input because it affects the input. The stop push button is also another one. What else is at the input? A motor thermal overload. So motor thermal overload is also at the input. This is how you do your design in a proper manner. Do we have any other? I don't see any other from the list provided there. Then you look at the output. So the output here is what would be connected to the, that's all you just check. What would be connected to the output? It's the motor run contactor. The motor run contactor. Because remember we said if you have the output like that, then you have that output module, then you connect your output there. So the motor run contactor is the output device. It's this guy here that's then connected to your motor. Okay. So those are the input and output field devices. Very important that you have that in mind. But remember, these devices need to be connected to the PLC. So we have to remember that to connect these devices to the PLC, because we want to come up with a ladder diagram, one of the one of the conditions or the rules of constructing a ladder diagram is that we'll have to provide a name for each of these devices as they are represented in the PLC ladder diagram. We'll have to provide an address, okay, to identify them, okay? So now we can now go to step 2, step number 2 now. So allocate or assign, let me use the word assign. Assign address locations for the inputs and outputs. Okay, we have to assign them addresses. Now, again, I mentioned this and I will mention it again just for the sake of those who missed it. Different PLC manufacturers will have different methods of providing the memory address locations, because these address locations are simply memory address locations. Okay, so you have to provide memory addresses. Now, Siemens would use a different memory addressing system from Allen Bradley or Mitsubishi or Omron. But whichever PLC you use, the addressing system, as long as it's consistent, it's not a big deal, okay? But you have to provide the address. Whatever method you decide to use, that's your own. I cannot penalize you on your method of addressing as long as it is consistent. So, because we appreciate that different manufacturers will have different addressing systems. So, for example, whereas an input, so like, let me just start again. Let's do what step number 2 requires. So, remember you have to provide a name, you have to provide an address. It's important. So let me just have our devices here. So let me have name, then we have the address. I don't know whether address is double D. Okay. And let me even have the wiring, the PLC wiring. How do you wire it from what we have discussed? Okay. So let's start with the inputs. We'll even do for all of them. So please remember our inputs we've listed. The start push button. Of course, you can't write start push button in the PLC, even when you're using your software. It's too long. So this is an arbitrary way of just assigning. You can decide to assign your own way. So you can say to mean motor 1 start, because you have the first motor. Remember, your design can have 2 motors, 3 motors, 4 motors. So M1 would mean the start push button for motor 1. You could have motor 1 stop push button for motor 1. You have the thermal overload. So you can say thermal overload for motor 1. Okay. Now, somebody can decide, no, I want to say push button 1 to mean for the start push button. Push button 2, that's the stop push button. Then maybe I just want to use OL to mean the thermal overload. So again, remember, you have because of the different manufacturers, and we are only teaching you the principle of doing this, you can use any different assignment, but as long as that assignment that you provide for the addresses is consistent, we have no problem. Now, remember, this is just the name. This is not the address. So each one of them must have an address, a physical location for the memory, so that the processor during scan cycle will know I need to go to this memory location, pick the logic state that is there, carry out an instruction, execute it, then I update. So you can say, some PLCs, like in this case, would say input 1.0. Then I'll call this input 1.1. Then I'll call this input 1.2. Okay, I know the start push button is a normally open contact, so the symbol will have to be a normally. Then the stop push button, the state is normally closed. That's how it's wired to the PLC. And then the normally the thermal overload is also normally closed. That's how it's wired to the PLC. Again, somebody can use a different address system. Somebody can decide, okay, for me, my addressing is going to be I 0.0, I 0.1, or even I1, I2, I3. Okay, even I1, I2, I3 is fine as long as it's consistent. Now remember, the address systems are 8 bits long. So you can have from I1.0 to I1.7. Then you need to move maybe to I2.0 to I2.7, so that each of the addressing system is 8 bits long. But I don't think we'll have scenarios where we have so many symbols or so many devices, inputs and outputs that exceed 7 and so on. But they might be there. Okay, so that's for the input. But remember, an address system must exist. So the outputs in our case here was just for the motor thermal, the motor run contactor. So for our output, we can say, I'll just put it here, motor 1, run. So that's the output. And I'll give it an address. The address has to be different. So I can say 1.0. So notice we are starting from 1.0 because that's the first location of the memory. Because the memory, I told you, is probably 8 bits for some devices. So this is 0.0 or 1.0, then 1.1, then 1.2, up to 1.7, so that you have 8 bits or 8 memory locations. Then you can, if you want to incorporate another, then you have to go to 2.0, 2.1, and so on. So this can be O 1.0. I know that other manufacturers will call it Q. Others will call it a different thing. No problem, as long as you are consistent with it. And remember, again, this is an output. But what kind of output? For those who have been in class before, we've seen that an output can also be a normally open contact or a normally closed contact. So this output is normally open. For those who have forgotten, please remember, we said that there are 2 outputs here. We can have, this is a normally open coil. Okay, not a contact, it's a coil. Normally open. Contacts are inputs. Coils are outputs. So the normally closed coil is like that. Okay? Where whatever state was at the output is negated. So if this was 0, then this one is 1. Okay? But in our case here, it's a normally open coil. Again, remember, coils are used to refer to the outputs. Contacts are used to refer to the input. So at least we have listed the most important, or at least the ones that we'll definitely require. We've listed them, we've provided the address. Now, because you have put your house in order in terms of design, it's now easy to start visualizing what needs to happen and what needs to go where. So we need to draw our ladder diagram. Now, it's very typical to remember that once you have done quite a number of designs, you know very well that, okay, I'll have to have my start. Let me draw this because these are field devices. These are not part of the PLC program. So you'll have maybe your start push button there. Okay. Then you'll have the stop push button. I told you again, these are just, it's like you're wiring physical devices to the PLC. So it's never considered as the part of the PLC program. We only draw this so that the illustration is very clear, especially for beginners who are trying to come up with ladder diagrams. Okay. But once you are very conversant with what you're doing, then whatever I draw on the left side and on the right side really do not form part of the PLC. The PLC only begins when we have this, when you now have this part. Because we had said that a PLC ladder diagram consists of two rails. So once you have two rails like that, then now, and then you have rungs. But otherwise, everything that falls on the other sides are just field devices. Okay? So, in this case, we are controlling a motor anyway. We'll see how that connects. So remember, from what we have done, you have to say this is a start push button. Because we are beginners, we are learning everything. Later, we might not be required to draw the things that I've drawn in green. So if this is a start push button, we know it as a normally open contact. This is a stop push button. This is a stop push button. It's normally closed. And this is the thermal overload. Okay. The address system we have agreed is I1.0. So this guy is I1.0. This guy is I1.1. And then this guy is I1.2. Okay. Again, very important. I'm trying to be as slow as possible just to make you understand. But if you are to do this on your own, you're expected to do it very fast because everything is in your mind and you're not explaining it to anyone. You're simply transferring that information on a piece of paper. But for our sake here, because we want to understand, we move step by step and we put everything in order. Now, remember, we are wiring field devices to a PLC. So it means now we must have the PLC symbols, the part that forms the software. The part, remember, these were hardware. This, I told you previously, this part is hardware. The other part is hardware. What falls in between here is the program or the software. So now that's what we need to work on, the software. Okay? Good. Now, remember, some things are very, very easy. We are supposed to draw a ladder diagram that controls a motor, but make use of the hold-in logic. Make use of the hold-in logic. So that's where now you have to think. We know a hold-in logic circuit should look something like this. Just a quick drawing. A hold-in logic was something like this, if I remember correctly. Okay. Something like that. So you have your A here, you have your B, you have your Y, and this is also Y. Okay. A is responsible for making this go to logic 1. B is responsible for returning this back to logic 0. And Y is responsible for holding on the state of the output, even if the input has been, the stop push button has been switched off. Okay. So have that in mind. But again, we are controlling a motor here. So the I1, which is the start push button, needs to be connected to its symbol, which is a normally open contact. And that normally open contact is M1. We had called it M1 start. And the address was I1.0. I 1.0. Okay. Now, we've seen how we control a motor before. So that we can stop the motor, we need to connect this in series with M1 stop. And we are connecting in series because the moment we press the stop push button, the logic for M1 stop should be 0 so that the output becomes 0. So this is M1 stop I 1.1. Okay, I'm going to send you a proper drawing for your visualization. Okay, so now you have M1 start and M1 stop. But the M1 stop is also connected in series with the thermal overload because we expect that in case of temperature increase or a threshold has been exceeded, then we expect that the motor stops immediately to protect its windings. And so we expect that we also connect this in series. Remember, if we connected them in parallel, it would be an option. Remember, if it's connected in parallel, it's OR. If connected in series, it's AND. So the AND function ensures that that input must be a logic 1 or must be considered. The OR is, an optional path for the logic to follow. But the thermal overload is not an option. The stop is not an option. The start is not an option. And then, of course, you have to have your output, which we had said was M1 run. Okay, there's the O, it was O 1.0. Okay, O 1.0. So, again, remember in our mind, we are supposed to incorporate this motor such that we have a hold-in logic. The hold-in logic, definitely, I told you, is connected, is branched out to the input, which is the start push button. So you branch out the hold-in logic like that. We'll see whether this works. Of course, then you have your output field device like that, connected to your motor. And this is O 1.0, okay? O 1.0, like that. So now, let's see. I remember I mentioned also one of the other rules that's very important for the PLC is that you have to write your comments. Now, writing comments here would be very difficult. So step 3 is you have to write your comments. Oh, step 3 was to draw the ladder diagram. Step 3 was to draw the ladder diagram. This is a very simple ladder diagram, but we are going to build on it as we go along. And then step 4, you have to make comments. So in our case, we can see, and we first of all need to check whether our ladder diagram works. So think about it. Initially, the start push button is not pressed. So it means it's transferring a logic 0. So this guy is at logic 0. Initially, the stop push button it's a stop push button. It's closed. So it's transferring a logic 1. So at the output of this, we have a logic 1, because if you were to view it in a software, or if you're writing the program, this would be green because already the stop push button is closed. So the M1 stop would be green in color because it means that it's already passing a logic 1 to the the M1 stop button is activated. So that would be a logic 1. Number 2, the thermal overload would also be green in color because it would be a logic 1. Why? Because already the thermal overload is in the closed position, meaning that it is already having a logic 1 being passed to the symbol itself. So you have a green. So you'd be having this as green and you'll also be having this as green. But the rest would be black or whichever other color, meaning they are not active. They're not active. It's only M1 stop that would be passing logic, and M1 toll, which is the thermal overload, that will also be passing logic. I hope that's clear, because I also don't want to keep drawing them in green and red. It takes a lot of time. You should now understand what I mean. So we have just said that in the initial stage, we have the start as 0 logic, is not passing any logic. The stop is passing logic 1. The thermal overload is also passing logic 1. And of course, we are assuming that initially we are having logic 0 here, because there was nothing put there initially. Now, from the logic expression that we said, you can clearly see that this is if we had put it initially. Let me use a different marker. We had said, I don't know whether I can expand this for proper viewership. We had said that the expression is obtained by saying if, then here we have or, and then here we have and, here we have and of course we have and. No, this is then, because we already at the output. This is then. So this is then. Okay. So we are having if the start, if start, or, again, remember how the scan cycle moves, or, and I didn't label the output here. This output, I should have labeled it. Sorry, I also didn't label the output. I should have written here. Please note that I should have written the output here as M1 run, and it is also 0, 1.0. Why? Because the output is branched to the input. So it's the same memory address. So whatever logic is here is the same logic that we expect here. Okay? Whatever logic there is what we expect here. So, but the expression would be if the start, or then we have the M1 run, okay? Or M1 run, and M1 stop, and, okay, and M1, no, M1 toll, then M1 run. Okay, sorry, the space is not enough, but you can see that what I'm saying is if during the scan cycle, you're expecting it to come from the run, come and check what this input is. Then it will have to come and check what this input is before it goes to this input, then this, and then move like that. And then it will have to repeat, because now the scan cycle ends here, because that's the last output. Remember, from left to right, top to bottom, but we have only one rung here. So it will have to scan through M1 start, then M1 run, then M1 stop, then M1 toll, and then provide M1 run. Now, at the end, once it reaches the end, remember, as it was scanning through these states, it was picking up their logics. And because the inputs are instructions, it was picking up those instructions. And then it was just noting what the output state was. But once it completes the scan cycle, because there's no more place to go, then it now updates the state of the output. Okay? So because I don't want to make this so congested, let me go back to what we were doing. Okay, so we said now that we have to check whether this works. So let's think about it. Initially, we've agreed that based on this logic expression, the output here is 0, based on the logic expression. Because anyway, if you check, 0 is already here. The start is already 0. So remember, every time the start is 0, we'll be having 0 or 0 and 1 and 1. Because we already have a 0 here, the output is going to be a 0. And so the motor does not run. It stays as is, which makes sense. But the moment the motor is pressed, the moment the start push button is pressed, so if you press this button here, it now changes to logic 1. And therefore, what happens is this state here will now change to logic 1. So now we'll be having a logic 1 here. When you press the start push button, you'll be having a logic 1, 1, 1. And because you have a logic 1, 1, 1, because remember the stop and the thermal overload buttons are still in their closed position. So you'll be having 1, 1, 1, which is providing a complete path for the logic to flow to the output. And so the output will also change to a logic 1. Because now there's a complete path for logic to flow all the way to the output. Even if the one down here is still 0, no problem. So during scan cycle, remember, it would be having if, let me even remove this. During the scan cycle, it would be having if the start push button would be 1, or this one would be 0, but that's an alternative path, it doesn't matter. The M1 stop would be 1, the M1 toll would be 1. So then the output would be 1. And then the motor would start running. Because once it completes here, the scan cycle is completed at the end of the last rung, and there's no other rung to be considered, it updates the state of the output. And so this would be updated to 1. And once it's updated to 1, what happens? The motor starts running. As soon as it's updated to 1, simultaneously, this output here the input is also updated to 1. Because remember, as soon as the scan cycle updates the output, it's the same memory address location as this input here. So because this input is the same memory address location as the output, as soon as the scan cycle updates the M1 run output, then the M1 run input is also updated as a logic 1. But remember, the person who presses the start push button does not press the start push button and holds on to it, because then you'll be there the whole day. You expect that you press it and then you withdraw your hand. So because he pressed it instantly, and then all the scan cycle, remember, happens in milliseconds, the output is translated to 1 and the motor starts running. What happens then is the start push button is no longer pressed. So it goes back in the open position. So the start push button has gone back to the open position, meaning this guy would go back to 0. Because you don't expect to press a push button and hold on to it. You expect that you press it and you leave it. So because you press it the first time, it brought in the chain reaction where the motor started running. And then when you remove your hand or you withdraw your hand from the push button, then M1 start goes to logic 0. But remember, we will be having this as logic 0 now. Start has gone back to logic 0. But M1 run is logic 1 from the previous state. It's logic 1. M1 stop and M1 toll retain their status. Nobody has touched them. And so because there's another path, in this case now, the scan cycle will see that the path for logic would be from here, coming down here, then it will be going. And so we're still having a complete path for the logic to flow through. And because we still have a complete path for the logic to flow through, the output remains as logic 1, and the motor continues running. So you can see that the motor will continue running even if the start push button has been released. The motor will continue running. Now, if you see that explanation, you can see that initially we made the motor start running. So the output went to logic 1. Okay, we made the motor start running using the start push button. And then, of course, because we didn't hold our hands at the start push button, even when we released it, because of the M1 run branch input that we have, the motor kept running. So we held on to the state of the motor, which is logic 1. Remember, the latching was you take the output to logic 1, retain that state or hold on to that state until something happens or until an instruction is given for you then to return the state of the output back to 0. So we've reached the state where 1, we've made the motor run. Number 2, we have ensured that the motor continues running even when the start push button has been released. Now, the only way this motor will stop running is 2 ways. One is if I decide to press the stop push button. Because if I press the stop push button, I will break the contact here. And if I break the contact here, remember, if the contact is closed, it's logic 1. If it's broken, it's open, so it's logic 0. So if I break the contact here, then this guy will go to logic 0. As soon as the M1 stop goes to logic 0, you can see that the output will definitely go to logic 0. And as soon as that goes to 0, this will also go to 0. So it will not matter even if the thermal overload is on, and we'll make sure that as long as one of the inputs is 0, the output would be 0. So the only way to make the motor stop running is to press the stop push button. And that is the other condition that's the condition we are referring to, or the instruction we are referring to, that removes the state of the output from a logic high back to a logic 0, from a logic true back to a logic false. So basically, you can see that this is a hold-in logic, where you can make the motor run, then it holds on to the state of running up until a stop push button is pressed. That's when it stops running. Of course, the same principle works with the thermal overload, but the thermal overload, it's not our action. It's an inbuilt action where, again, if it senses an over temperature, then of course it breaks the contact. So if it breaks the contact, again, this will go to 0, and of course the motor will stop running. Okay, but that's an inbuilt function. Okay, it's not controlled by us. So this is how you come up with a circuit that, or a ladder diagram that works. So remember, I said step number 4 was to write certain, let me look at time, 1 hour is gone. We expect to write comments. You can't expect me to understand. Okay, go ahead.
I thought the stop push button contact and the thermal overload contacts should be normally closed. You kindly explain the logic behind using the normally open contacts.
All right. Did you come in when we started the class?
Yes.
All right. So it means a few people still don't get it. Okay, let me explain that. Guys, this is a very, very important concept, and I expect all of us to remember it. You see, this whole diagram here is part of the PLC. Okay? It's a whole PLC system. But the part that we connect in here is just the program part. Even in the lab, you will see there's the program part where you use your computer to put in the symbols. But then there's the part where you have to connect some wires. Though the connection is not too much like the other normal relay circuits, we just connect a few devices here and there. So it is important that we remember at this point, it's important that we remember that we understand how the PLC inputs work and how we combine them with the PLC symbols. Now, Let me go back to the question. The student is asking, why are we not using a normally closed contact for the stop push button and also for the thermal overload? In other words, why are we not saying that this should be a stop push button and we also say this is a stop push button? Now, the only way to explain it is, okay, let's make them stop push button and see the principle of this. Let's make them stop push button. And then maybe that way you will understand. So we have said, okay, because the stop push button and the thermal overload are normally closed contacts. Now we've made them normally closed contacts like you wanted. Now let's see what happens to our circuit. Remember, we have field devices, which is the start push button, the stop push button, and the thermal overload. Those ones are connected using wires to the PLC, and then the PLC is connected to the program, and then the program has an output module that is then connected to the field devices. So now, okay, I'll stop admitting people at stage. So now, if you look at the instructions that we have here, we have agreed, okay, let's use the normally closed contacts, as you say. Now let's look at the logic using those normally closed contacts. The start push button is still open, meaning the contact is not made. The contact is not made there. What that means is that this guy is simply open. And so this, we say this is an input module. And then this is the output module. Now, the input module is the interface between a field device, which is a physical device, and the software part, which is the PLC diagram. So, because the start push button is in the open position, the input module will tell the corresponding start push button that the logic that we have currently is a logic 0 because it is in the open position. So the start push button, which is now the symbol, will know that we have a logic 0. So it is not activated. I don't know why students are coming now and they're interrupting my class. It becomes very, why are these guys coming to class late? So now, because the start push button is at logic. Yes. Yes.
Or the slot for the class was 8 to 9. So when 9 reaches, I think when somebody drops out, we cannot come back to the meeting.
Oh, so it dropped everyone out?
No, when you lose connections, you can't come back to the meeting.
Oh, okay. Also, it's a case of then you look, because I was wondering, maybe, okay, so if you lose a connection, then I have to readmit you. Okay, thanks for explaining that. That's fine. Okay, so now I understand. I have to readmit them because I was wondering why they're coming so late. Okay, so let's continue with the explanation. We have said we are trying to explain why we have decided, hey, maybe I should just take a minute to allow these guys who are dropped off to come back in. We are trying to see what will happen if we actually make the symbols, remember, we make the symbols of the stop push button and the thermal overload, we make them normally closed. But remember the connection that's also done to the field device. The field device is usually, a start push button is always in the open position until it is pressed, then it is closed. The stop push button is always in the closed position until you press it, then you open it. And that's the same thing with the thermal overload. So look at this. If initially the start push button has not been pressed, we are going to have a logic 0 being transferred to the symbol, the PLC symbol itself. So if you have a 0 logic on the normally open contact, you get on the output a 0 logic. Okay, so the only way to have a logic 1 being transferred from the normally open contact is to give it a logic 1. Okay, looks like a lot of people dropped off. Omolo, your hands were up. I don't know whether you have a question even as we go on, or it's the one that I'm trying to solve. Okay, so now again, work with me slowly, but make sure you understand. Because the start push button has not been touched, it's simply transferring a logic 0. It's interpreted as a logic 0 at the symbol, at the M1 start. So M1 start only receives a logic 0 because the start push button has not been pressed. So M1 start has a logic 0 transferred out of it. Hope that is okay. Now, remember, we've not touched anything. We've just connected the circuit. The stop push button is always connected in the normally closed position, meaning it is until you press it, that is when you break the contact. If you don't press it, the contact is made. It is closed. It's like a switch. So the switch is closed up until you press it. That's when it opens. That's when it breaks the circuit. So the input module will translate this as a logic 1 being given to the M1 stop, because this one is connected to the M1 stop. So remember, we have in this case, we have a stop push button that is normally closed, and it is given a logic high or a logic true or a logic 1, meaning it is activated. How does a normally closed contact behave? The behavior of a normally closed contact from our discussions previously is that it is always passing logic until you activate it. The moment you activate it, then it now blocks logic. That is how it works. So the normally closed contact, if it is not touched, then it is always green in color. But when you activate it, then now it's black in color, meaning it is now blocking logic. When it is green, it is passing logic, meaning a logic 1 is seen at its output. Okay? So now, with that analogy, look at the stop push button. It is already in the closed position. That is how they come. That is how the manufacturers make them. It's already in the closed position. So therefore, the translation is that a logic 1 is pushed to the M1 stop. And when you push a logic 1 to the M1 stop, it is already in our case here, it is already closed. So if I activate it, what happens to the normally to the stop push button? Because if we have a logic 1, there, it means I am activating a normally closed contact. If you activate a normally closed contact, it passes a logic 0, meaning it blocks logic from passing through. If you want a normally closed contact to pass logic, you should leave it deactivated. You should leave it as a logic 0. You should leave it untouched. Then it will be passing logic. If you activate it, if you give it a logic 1 or a logic high, whichever it is, then it will now start blocking logic from passing through. So remember, without touching anything, just by the virtue of connecting this circuit as is, we have seen that the start push button is a logic 0. The stop push button is already at logic 1 because it's a closed position, meaning you're already activating the normally closed contact that you have here. When you activate a normally closed contact, it's like a NOT gate. You give it a logic 1, it gives you a logic 0. You give it a logic 0, it gives you a logic 1. So in this case, we have given it a logic 1. So it is giving us a logic 0. And because this is also a normally closed contact, you give it a logic 1, it gives you a logic 0. You give it a logic 0, so in case there was a thermal overload, in case the temperature exceeded a certain threshold, then it breaks open. But in this case, we are assuming that it is not breaking yet, so it's giving a logic 1 because it's closed. It's a normally closed contact, meaning in the normal condition, it is a closed switch. So right now, it's in a closed position. That's why I'm putting 1 there. And what happens when you give a normally closed contact a logic 1? It gives you a logic 0. So you can actually see, by virtue of not touching anything yet, by just connecting the circuit as is, everything here is a logic 0. Everything is a logic 0. So, do we already see a problem with that? If we don't, we'll see something shortly. So if everything is a logic 0, then we have a logic 0 here. So the motor is not running. But now let's see. Let's then decide to press the start button. Let's press the start button. So the start button, let's say, is closed, meaning now the start button is given a logic 1. So the start button, now we have a logic 1 because the contact is now closed, which is translated as a logic 1. So what that means, therefore, is that that logic 1 would be communicated to the symbol here. So that is the logic 1. Remember, we have connected our stop push button and our thermal overload to normally closed contacts. So see what happens. Because these ones are still a logic 1, because it's closed, then this is still 0. The M1 stop is still 0. Because the thermal overload is also still a normally closed position, so it's closed, meaning it's at logic high, then of course the symbol is also 0. So I've pressed the start push button, but you can clearly see that there is no path because this one takes the state of the output. You can see that even after pressing the start push button, it is only the M1 start that is on or having a logic 1. The rest are a logic 0 because we made them normally closed contacts. So I expect that if I press the start push button, the motor should run, the output should be 1. But in this case, even when I press the start push button, you will see that the output will remain at 0. So the motor will not run. So what's the use of having a start push button that even when pressed, the motor does not run? And the reason the motor is not running is because we have not connected our ladder diagram properly. So I'll go back to the state of where we now connect them in the normally open position. So let's connect them back to the normally open position. I'm willing to take as much time on this so that you understand. Otherwise, there would be no need to proceed. So let's say we have broken this. Now we have made them normally. Okay. So clearly what happens is, ladies and gentlemen, because in this state, we'll be having the first start push button, logic 0, because it's open. The stop push button is logic 1, because it's in the closed position normally. Then the thermal overload is also logic 1, because it is always closed. It's a normally closed contact. So in a normal condition, it is closed. Now, let's see those logics being transferred to our symbols. 0 is transferred to M1 start because it's the same memory location. So we'll have a logic 0 on the start. Remember, my friends, the same memory address for the start push button is the same memory address for M1 start, the symbol. So it means the logic that you have at the point of the start push button is the same logic that you need to have, is the same logic that's provided to that start push button. So if you have a logic 0, it means the M1 start is deactivated. If you have a logic 1, then it means that it is now activated. So logic 0 means deactivate the M1 start symbol. or the contact. Logic 1 at the start means activate the M1 start contact. And being a normally open contact, when it's activated, it transfers a logic 1, meaning it allows logic 1, a logic to pass through it. So here, because the start push button is in the open position, the M1 start push button remains deactivated. There's no, it's still open. It's not allowing logic to pass through. So at its output, we are having 0. The stop push button is in the normally closed position. What that means is the input module will tell the processor that the logic 1 we are having here means activate the stop push button, the contact. So this guy will be activated. Activating means you are energizing it. So when you energize the M1 stop button, remember it is in the normally open position. We have removed the normally closed contact that we had. Now it's in the normally open. When you activate a normally open contact, what happens? It allows logic to pass through. So you are having a logic 1 passing through. The normally closed contact of the stop push button is the same thing of the thermal overload, sorry. So the thermal overload also is at logic 1 normally. And so the input module will tell the processor that go to the address for the thermal overload and activate, meaning whatever was there, the logic that was there as 0, make it 1. So the logic that would be here is 1. Okay? So I didn't know that extending this class will bring a lot of trouble, but anyway, it's fine. So originally, without touching anything, without pressing any button yet, we are having M1 start at logic 0. It's not passing logic. M1 stop is already passing logic, meaning if you are observing it in a computer, it would be green in color. It would be like that. It would be like that. And the thermal overload would also be green in color. It would be passing logic like that. So those two would be green in color. Why? Because their field devices are in the closed position. And being that we have used the normally open symbols or contacts, then they will be green, they'll be activated. And so once they are activated, this would be the original position. But because of the way we have connected our circuit, we'll be having 0, 1, 1. So the output would still be reading 0. There would be nothing. Because for the output to be 1, you expect a complete path of logic up to the output. So we don't have that complete path. Even this one is still 0 because we've not pressed anything yet. So it's like if you go to memory address I1.0, you'll find logic 0 there. If you go to memory address I1.0, for the stop push button, you will find, I think this should be 1.1, I think. I'm the one who changed them. This should be 1.1. This should be 1.1. And I think this was 1.2, if I was not wrong. Okay. So if you go to memory address I1.1, you find a logic 1. Memory address I1.2, you find a logic 1. Memory address O1.0 is logic 0. Because the output here is only branched out as an input, but they're the same memory location. So it is in this state that if now you decide to press the push button, you press the push button so that now you have a logic 1 there, then of course this guy will be translated to a logic 1, meaning the M1 start push button will now allow logic to pass through because we've pressed the button. So momentarily, when you press that button, the M1 start becomes a logic 1. And then now you can see that we have a complete path, and therefore the output will definitely change from the logic of having 1 and 1 and 1. 1 and 1 and 1 should give you a 1 at the output. And the moment you get a 1 here, then of course this guy also because it's the same address. That guy also becomes 1. So you can see that the motor would be running. So the condition for the motor to run is that we have a complete path for the motor, for the logic to flow from the input to the output. So as it is, then the motor would work. So back to your question. In isolation, if you were to use an M1 stop push button on its own, then we would use it like that. Remember, remember the hold-in logic. We had a normally open contact and a normally closed contact, and then we had the output, and of course, we decided to branch the output like that. So this was A, this was B, this is Y, and this is Y, okay? So here, it assumes that this guy is independent on its own. It's just, we are trying to understand the principle of operation. But remember, ladies and gentlemen, that in our circuit here, it's like having, let me just put it. For the start push button, we have, maybe this, if I draw it like this, people would probably understand better. For the start push button, you have something like this. From the field device, and then the symbol. So this is like a start push button. So this is the field device, which is in a normally open position, and this is the symbol that we have, the contact itself. So this is the contact, the PLC contact, and this is the field device. Okay? So you can see that this one will work. If I provide a 1 here, it will also push that 1 to this guy, and this guy will also push 1 out. Meaning, if I provide a logic high here, then it activates the next one and gives it a logic high, and then it passes out. But now let's look at the stop push button. The stop push button, first of all, in this case, you can see it's in the closed position, so it's like this. And then the symbol that's connected to it is like this. So this guy is already passing a logic 1. This guy is already passing a logic 1. So if it is passing a logic 1 here, it means this guy should be green in color, like that. So that we know that this is already a logic 1 also being passed at the output. And that's the same thing with the thermal overload. So here, I'm only considering it as an independent device. But here, you can see there is the field device, the physical push button, and then there is the contact, the PLC contact itself. So because the field device is already coming from the manufacturer as a normally closed contact, we use the PLC contact as a normally open contact. Then it will work. Because if we make the mistake of having a normally closed contact as the field device from the manufacturer, because the buttons are already standardized, manufactured as closed contacts. And then we also decide to use a PLC closed contact like that. It means that this guy already, because it's closed, it's passing, it's closed. So it's already at logic 1, okay? Meaning, if you have the contact as closed, it's already at logic 1. So before activating it, it's already passing logic. And then, so if it passes a logic 1, and this is like a NOT gate, what happens? You get a logic 0. Okay? Because it's like you're negating twice. So you already have a device that's giving you a logic 1. So if this logic 1 activates the next normally closed contact, it then gives you a logic 0. Because a normally closed contact, when activated, it blocks logic from passing through. So the idea here is, because we already have a normally closed contact here on the field device, it is only necessary that we make this a normally open contact. Because we already have the thermal overload as a normally closed contact, we expect that the thermal overload symbol, the PLC contact, becomes a normally open. But if you were to consider these in isolation, forgetting that we don't have field devices, so let's say the field devices are not being considered, we are only considering the PLC program, then we would represent it as a normally closed contact. So here it's like we have not connected it to anything else. So to understand the principle of operation of a normally closed contact, we can use it on its own like that. Or alternatively, we can use in its place, we can decide, okay, we don't want to use it there like that. We want to use it like this. We want to put a normally open contact, but we know that we have a normally closed contact connected to it somewhere. So if this was B, then we know this is B. I hope that makes sense, my friends, because otherwise we will not proceed and understand anything. The idea here is we are connecting, and I think I'm going to put that in bold in your notes that I'm going to send you after this, that the rule of thumb is that we must make sure that when we are connecting the PLC input devices, the field device is in the normally closed position. So the symbol that we use within the PLC should be in the normally open position. Because if the field device is in the normally closed position, and then the PLC symbol is also in the normally closed position, we are going to negate the whole process, and therefore the output will always be zero. Even when you stop the motor will not stop. It will continue running, because you're negating that process by having two normally closed contacts connected together. Because remember, in the PLC, you have to actually connect this device using a wire to the input module. Then it is the input module that is connected to the M1 stop. I mean, this one is connected to the M1 start. And then the stop button is connected to the M1 stop, like that. But we have to physically connect these devices. But these devices come when they're already manufactured. The start push button comes when it is a normally open contact. The stop push button comes when it's already a closed switch. The same thing as the thermal overload switch. So we have to consider the state of the field device, compare it with the state of the symbol. If we didn't have the field devices, then we would just make these guys normally closed, we are done, we move on. But because we know how the field devices come from the manufacturers, we have to consider that when doing PLC wiring. So don't just wire these things abstractly without thinking about it. If the field device comes as a negated device, then you have to use the normally open contact as a symbol. If the field device was not there in the first place, then just use a normally closed contact. There's no problem. So I don't know whether that explains anything or I need to do that again. Are we fine?
Okay, yeah, thank you.
Yes, please. It's a very, very good question, because over the years I've seen a lot of students make mistakes. But that's why I was telling you, the more you interact with all this stuff, then we are fine. So in closing, because now we've spent a lot of time on it, I will not be able to go to the next part that I wanted to talk about. In closing, ladies and gentlemen, if we were to understand PLC ladder diagrams on their own, okay, the hold-in logic, let me just go back to the hold-in logic circuit, because that's what we were trying to achieve, the hold-in logic. We know that the hold-in logic requires a normally open contact with a normally closed contact, and then connected to the output, but we branch that output to the input. Then we'll achieve the hold-in logic. So this is A, this is B, this is Y, and this is Y. So because we are discussing a hold-in logic, we are not discussing the downstream or upstream equipment of devices. Remember, we are using a normally closed contact because we are strictly talking about the PLC. So in an exam setting, if I don't ask you to include, remember, in an exam setting, remember the question said, incorporate a start push button, a stop push button and a motor thermal overload and a motor run contactor. It's indicated, meaning you have to draw them, you have to incorporate them. That's why we had to draw them. And because we had to incorporate them, it changed how our ladder diagram looked like. If I didn't say, if the exam did not ask, or if you are not asked to incorporate a start push button and a stop push button and a motor thermal overload as a field device, then our circuit, remember, if those devices are not being considered, then our circuit would be like this. If we were not asked to consider the field devices that I mentioned, our circuit would be like this, and it would make sense. Because we would not, the circuit that we've just drawn for the motor control, okay? So the circuit for the motor control would just be like this. And then, so this is the start, this was the stop, this was the thermal overload, and that's the output, and that's the output. So remember, here we are not considering the state of the output device, the field devices. So that if I were to explain how this thing works, then we are only explaining it from the position of the program itself. But because we are to do things in a real world scenario, we know that a start symbol or a start contact is going to be connected to a start button. And a start button comes when it's already an open contact. So we are having a normally open connected with a normally open. So that's fine. That works. There's no problem there. The stop push button, if we were not to consider the field devices, then we just connect it like this. But because the field device we know comes when it is already closed, the field device comes when it's already closed. So it's already a normally closed contact. But you know it's connected to this guy. So it means we cannot close this guy. We have to open it so that then we have a symbol that is normally closed and then normally open. So this one can work nicely and it will provide us with what we need. And that happens again with the thermal overload. That also happens with the thermal overload. So in this case, and in most cases that we are going to talk about, they are practical designs. That's why I was saying, please remember, in practical scenarios, which we are going to deal with a lot, you must have a rule of thumb to remember every time. And what you're supposed to remember is that the stop push button and the thermal overload are always wired in the normally closed position when they come from the manufacturer. So if we were to include them with our PLC inputs, then our symbols are going to be normally open. Our symbols have to be normally open. So please take note of that. Again, I think I'm going to put it in uppercase and I put it in bold in the notes so that you always remember that. You don't make that mistake when you encounter real world problems. So basically, I've smudged my diagram as much as I can to just try and explain everything. But we can now see that the first part is we have just used a normally a holding logic to latch onto the condition of the motor, that is to run until we press a stop push button. So this is basically a latching circuit. So this is a typical latching circuit, but it's one that controls a motor. It's one that controls the operation of a motor. I told you I wanted to move on to the same question, but to a different scenario. So again, let me conclude. I said step 4, for those who probably were writing. In step 4, comment on the ladder diagram. Very, very important that you have to provide comments on your ladder diagram. Comments on your ladder diagram. Very important. So the comments don't have to be so wordy. You could just be providing basic information that somebody reads through and understands. Okay, so maybe you can say something like that M1 start, okay, push button is used to activate the M1 start push button input, because it has to be the input, is used to activate the M1 run output. You can see that the condition for the motor to start running is that I have to press the start push button. If I don't press the start push button, the motor will not run whatsoever. Okay? Then the M1 run output, the M1 run output is used a second time to latch the M1 run output is used a second time to latch the M1 run output. I think this should be M1 run input. Made a mistake. Yeah. The input there is used to latch the M1 run output, so that no matter what even if you remove the start push button, we'll still have the motor running. Then, of course, the both M1 stop and M1 overload are wired in normally closed, or as wired as normally closed. You can indicate it there as normally closed. To the PLC input devices. Thus, are configured as normally open symbols or contacts in the logic. Very important. That's what we have been talking about for so long. Okay. Now, the latch is reset. The latch is reset. That's the last comment. You don't have to write a lot of comments, but they have to be complete. The latch is reset when either the stop is activated, that is, if M1 stop is activated, or when the logic flow is broken. Okay. So it's important that you always indicate a few comments here and there, and those comments will help somebody remember. Will help somebody remember exactly how your diagram works. How your diagram works. Now, I have taken a lot of time to explain this, which I don't mind, but I hope that the time that we have taken to explain this will bear fruit by at least you being able to completely understand how these ladder diagrams are constructed, so that it's not in vain. I wanted to move on because the next part of the question was to incorporate another thing. In this case, we are now expected for the second case, in the case that we were doing, that we introduce a warning siren in order that it lets the operators know that the motor is about to start. So that when I press the start push button, the motor doesn't start immediately. There's going to be a siren and a delay time. So maybe the siren will go off for 10 seconds, then the motor starts running. So that it's a way of warning people who are close to the motor, because some of these are very huge machines and you don't need to be close when they start because they are loud, that is, they are noisy, but also they could be dangerous. So we needed to incorporate a siren system such that when somebody presses the motor start push button, the motor doesn't start immediately, but the siren goes off for maybe a delay time of 10 seconds. And then after those 10 seconds, the siren goes off, but the motor now starts running. Sorry. So yeah, so I think you get my point. So you expect that when you press the start push button, then the siren would start going off. So people will know that when we hear that siren, we know that there's a motor that's about to start. So if you are close to it, we need to move away. So, and it gives you a delay, could be 10 seconds, 5 seconds, 15 seconds. And then after that delay has been achieved, then the motor starts running and the siren now doesn't have to continue providing the alarm. So that's what probably now we look at in the next class. And I think the best way now to proceed is let me send the class rep the notes. Let me complete the solution to the, I just want to add in the solutions to the notes so that you read them on your own, so that when we meet in the next class, at least you've had some knowledge of explanation, so that I don't have to explain everything from scratch. You'll have some knowledge, so I'll only explain a few areas that don't make sense, and then we can move faster than this, because we need to move now into the real world. So there are two scenarios that I need to bring about. Because of time, I'll just have to wait for the next class. So the first scenario is we want to introduce a siren system to alert operators before the motor starts running. So clearly we'll need another output for the siren, because the output needs to be connected to a siren. And then we'll also need a timer that now counts down the 10 seconds or the 15 seconds before the motor starts running. And then we'll need to go further and introduce another system that it's not only the siren that's going off, because not everybody, some people don't hear. So if the siren is going off, people are listening to it, those who can hear it. Those who can't, we need to introduce a flash warning system. There's a flashing system. So there's a light that needs to keep flashing again for a period of time, so that the siren, yes, is on, and the flashing system is on, so people can see and people can hear. Then the motor is triggered after those conditions are met. So these are just ways of trying to improve on the original system. Remember, we just started with how to make the motor run, then how to hold on to the state of the motor running up until somebody presses the push button. Then now we want to activate an alarm system to warn people before the motor starts running. Then for people who don't have the capability of hearing, how do we activate a flashing system? So there's a siren system, there's a flashing system, then the motor is activated after those conditions are met. So the best way to do this is just to send you the set of the notes. You read ahead of me, especially because I told you next week I'm likely we might not have our classes. I'll confirm it over the weekend, but I was instructed that we expected to retreat to complete some course outline for the biomedical engineering course that we intend to introduce. So because I'm in that committee, I'll not be able to have classes, because we'll be having discussions the whole day. So I will update your class rep over the weekend, whether it's been postponed or if it's still active. And so I expect that during that time, if I'm not around in the next class, you guys will be able to read through these notes, so that it gives me easy time when we next meet to simply explain a few things. Okay? All right. Is there any question? Because I think due to time, There's no need of starting on timers at this point. It will not make any great value for us. Sasa unaweza uliza swali, just go ahead.
Okay. Hello, sir.
Yes.
So let's say you're programming it. Will you use the first method or the second method?
If you are programming it in the lab.
Yeah, let's say in step 7.
Okay. If you're using step 7, for example, and you just want to simulate the environment, let's say you're in your computer and you have the cymatic step 7, and sorry, I think that noise should just. So if you're in the lab setup and you're programming this, you can use the normally closed contacts because you're going to simulate to see how it works, okay? But if you are to connect this, if you're given a push button, a physical push button that you also have to connect to the input module, then you'll have to use a normally open symbol. You get what I mean? So that you have to you be aware of your design element. So if in the lab you go there and you're told, okay, you have to come up with a ladder diagram. These are the push buttons. These are the stop push button, the start push button. You'll also, you'll have to connect them physically. Those ones you have to connect physically with wires to the input module. And then, of course, now you proceed to doing your ladder diagram. Then it means you will have to use normally open symbols, normally open contact, because you have the physical field devices that you also have to connect. But if you are to just simulate this in an environment where you have the software and you just want to see how it operates at the output, then you will have to connect a normally closed contact instead. Because now you're not given field devices to connect. The reason why we were using the normally open symbols is because we are cognizant of the fact that you're given a field device that you have to connect to the PLC. And that field device comes with a certain position. The contact is already in a certain position. So simulation alone, where you want to see the results, use a normally closed contact, no problem. But if you're given field devices to physically wire to the PLC that you're also writing the ladder diagram for, then you'll have to make sure that now you use normally open contacts because you know the physical devices already are in the normally closed position. Sawa sawa?
Yeah, it's okay.
Good. All right. See, bado tuko na bado tutaangalia a few other examples together and we'll agree. And I'm also not mad. In the case of the exams, I'll definitely specify in case you are to incorporate a field device, I will tell you incorporate a field device. If I don't mention that, then you just use the normally closed symbols, no problem. But if I say incorporate this device, then you'll have to know that because we are incorporating these devices, I have to change my ladder diagram. But if I just want the ladder diagram without the field devices incorporated, then you can just use a normally closed contact, no problem. So I'll be very specific in the question and you will also have to understand it. Sawa? All right. And the reason is, ladies and gentlemen, not all input devices are start push buttons and stop push buttons. There are certain other maybe setups that we'll see that don't need a start push button, and they also don't need a stop push button. So in those cases, we'll definitely use normally closed contacts because we are not, it is just that the start push button and the stop push button come when they're already in a certain contact position. But if the field devices that we are using are not start push buttons and they are not stop push buttons, they are other devices, maybe they are solenoid valves, then you see now we are not going to be using the setup as we have, because now they don't come with a normally contact position or a normally closed contact position or a normally open position. So this only applies when you're using a start push button and a stop push button. But otherwise, other input devices might not need you to have those contacts the way we have done them. That's why if it's software, just think of it as a normally closed contact. But if it's to be connected to a field device, then now you have to change your software aspect. All right, I hope that's okay. I think I'll query you again with some other examples to illustrate my point. Okay, guys, thank you so much for listening. I appreciate. I have another class in the next 9 minutes, so allow me to take a break for at least 5 minutes before I move on to the other class. Please take the notes from the CR, read them. If I don't see you next week, then I'll see you the other week. All right, goodbye.